Hello everyone, and welcome to a new topic, which is different techniques of image acquisition of this course, Remote Sensing Essentials. So in this particular discussion, we will be considering different techniques of image acquisition, how images are acquired, what are little inside, not really electronic part, but different types of sensors which we will be discussing. And the most familiar digital image is basically snapshot taken by a digital camera or a handheld camera, and which generates digital image that can be stored in a computer, displayed on a screen and printed. And this is the most familiar way we know in the digital images. There are some satellites also, like I give you the Indian example, the INSAT series of satellites. Currently INSAT 3D is in space. These are geostationary satellites. We have already discussed different types of orbits, so I am not going to go in detail about the orbit. So geostationary satellites, and this INSAT, and they are having digital cameras which can provide every half an hour an image of India and surrounding countries, and it is called India disk because it covers a circular area. There are various such satellites, especially the purpose of these satellites are either communication and for telecommunication, also television communication, but at the same time, since they are all the time looking towards India, they are geostationary. So these cameras, digital cameras, are also not the handheld which we use as a SLR or DSLR, but more sophisticated cameras have been installed and they have been programmed so they can send images every half an hour. This frequency can also be increased if required, especially for monitoring of cyclones and other things, but normally and generally they provide the data at every half an hour. But they are snapshots, they are not taken line by line or not done scanning as we see in case of a flatbed scanner on a photocopy machine also. Those are scanning devices, whereas these digital cameras or digital sensors which are on board, which takes a snapshot, are not really scanning devices, they go in just one go. And whereas the satellite images are they are also digital images like your snapshots, but they are taken line by line, scanned as the satellite move in the orbit, and line by line the data is recorded, and at the same time it may send towards the earth also through a direct broadcasting method, which we will be touching later in this discussion. So these orbiting sensing devices which are on board of satellites, and they scan line by line and build an image. Contrary to this, in your digital camera, it is a snapshot, it's just one go, in a few seconds, a split second, an image is captured. So the sensitivity and other things are different, the whole mechanism is also different. Now the sensors which we discuss in remote sensing, imaging sensors, which are nothing but an electronic device which produces an electrical output which is proportional to light intensity. So these are light sensitive sensors, and higher the light or reflection or emission, more the output it will generate and more the value it will record as a pixel value. So these are electronic devices. There are mainly three types of sensor are there. One is the single imaging sensor, another one is the line sensor, which is very common. Array sensors which you see is in most of these snapshot cameras which are using these array sensors. Since they are also on many satellites, so that has been included under this category. So single imaging sensor, a line sensor and array sensor. In case of single imaging sensor, just one single cell is there, or CCD you can say, the charge coupled device, and that takes the whatever the energy which is coming over it, a reflection or emission or whatever, and this converts to electrical currents, and higher energy means higher value, and so on and so forth. This is the schematic on the left side, whereas in the front side of illuminated sensor with a pixel size of 5.3 micrometer. So, very tiny electronic device is a single sensor. Whereas in case of line sensor, you are having array of such single sensors or CCD, charge coupled devices, arranged in a line. And like here, this is the real photograph, which is just 36 millimeter long, the total length here, and it is having 2048 CCDs arranged in a linear. So, if this is put on a satellite sensor, then an image width would be 2048 pixels width, and it would cover a quite large area from that distance, which is 940-50 kilometer away from. So, it is a solid state and a linear sensor, most common nowadays in the camera or sensors on board of different satellites. Now, for snapshotting devices or digital cameras which are on board of satellites, they use the 2D array, two-dimensional array sensor, which is in 2 dimension, rows and columns are there, and these CCDs are arranged in a 2-dimensional matrix. The real example is shown here, that matrix array sensor 16 by 10 rows and columns, which is 80 millimeter and 50 millimeter and multiply by 50 millimeter, which is the active senses area, which is this much. Now, in compared to the linear array which we saw, there where we had 2048 CCDs, but here we are having just a few CCDs arranged. I say 2 dimensions, this is just example of that. In case of single sensor, when it is used and either on a film or a sensitive electronic sensitive devices, when it is you are having a sensor, it rotates, this rotation is there and it keep recording the things. So, there may be a film or some other sensitive material. So, this is one image line out per increment rotation and full linear displacement of sensor from left to right. And such sensors are not there anymore now on satellites. So, most of the common one which we are having, the linear sensors. Using single sensors and the image acquisition, the most common sensor of this type is the photodiode, which is constructed by silicon materials and whose output voltage waveform is proportional to light. So, they are used for different purposes, but not really a serious remote sensing, and these single sensors are not used. Whereas, in case of this 2D or a linear sensor, in case of linear sensors, a different scenario is there. So, even if one is having single sensor, a 2D image can be generated by having this kind of arrangement of a rotating drum, and line by line, and that is the single sensor records the energy on a film or whatever material you are having. And a single sensor is mounted on a lead screw as shown here on the right side, and provides motion in perpendicular direction. And this is mechanical thing is there, and they are having their own difficulties, but trade off is they are inexpensive and one can acquire a high resolution images as well using even a single. So, low cost devices are possible. Now, this is the most common one, which is the linear sensor array. So, you are having just one line, and I already showed that on that one 2048 CCDs were arranged in a line, and here it moves, this is the direction of motion. Then the sensor strips can acquire the data of entire area as this strip moves, and which is on the satellites. So, this linear array provides imaging elements only in one direction. Motion perpendicular to the array provides imaging in other directions also. And this type of arrangement used in most flatbed scanners as well as on satellite sensors also. So, sensing devices with 4,000 or more inline sensors are possible. 2048 real example I also showed to you. One dimensional imaging sensor strips, these arrays respond to various bands of electromagnetic spectrum are mounted perpendicular to the direction of flight. So, they are fixed devices, no mechanical things, and their life is very good, very long, and performance wise they are also very good. And when we go for their data acquisition, this is how a single sensor will do. So, when you are having multiple sensors, same thing is repeated for 2048 times or 4,000 times depending on. So, when you are having just one single sensor, this is the illumination source, and that is the energy source, and then whatever the energy which is getting reflected here, which goes through this imaging sense system, which is this part, the C part, and then it is projected, and then it is recorded, and you get a output image, digital image like this. So, likewise these images are created. Now, this type of arrangement is generally found in digital cameras or satellite sensors. An example is InSat 3D, because they are taking just a snapshot. But when we go for a linear one, then it is this linear array is arranged in a manner that it is across the motion of the sensor or satellite, and therefore, it is possible to acquire images. The only problem with such linear arrays about the calibration of each CCDs. These has to be calibrated perfectly. That means their performance, individual performance should be matching with others. Otherwise, in an image, output image, you might be seeing some stripping effects, and which is very difficult to remove. So, that is one of the drawbacks in that one, because if an array, linear array is having 4,000 CCDs, then all 4,000 CCDs should have the same responses against a single object, a same type of object. So, this is the response of each sensor is proportional to the integral of the light energy projected on the surface of the sensor, and the function of all these should be very much perfected. And that is the calibration part is most important in linear array or any such sensors or devices, sensing devices which are put on satellite images. So, as you know that image is a two-dimensional matrix which is having if we define f function x and y, and the value or amplitude of f at a spatial resolution x and y row and column we can say here is a positive scalar quantity, that is positive integer value. So, f this becomes basically pixel value, which is nothing but the amplitude of the energy reflected or emitted which is being recorded. And when image is generated from a physical process, its value are proportional to energy radiated by a physical source. This is what the exactly is done in case of satellite based sensing. So, as a consequence, this f, x and y must be non-zero and finite, and this is not infinite. Remember, this is finite. The values, this radiometric resolution or number of bits are fixed before the launching of such sensors. So, whether it is a 6 bits, 8 bit, 11 bits, 20 bits, it is as per the design and requirement. So, this is 0 less than function x and y, and that less than infinity is here, but it has to be finite, that is why it is less than infinity. So, this function f, x and y may be characterized by two components. The first one is the amount of source illumination incident on the scene which is being viewed, and of course, the second one is the amount of illumination reflected by object in the scene. So, so these are called illumination and reflection components denoted I and R of x and y. So, of all individual pixels, these x and y would be there. So, I is the illumination and R for reflection respectively. Now, these two functions combine as a product to form f x y, and what we can write here that f x y equal to I x and y multiplied by I x y. So, it depends whether what we are having illumination and reflection. So, simple image formation can be that 0 less than I f x and y less than infinity, and 0 less than R x and y less than 1. So, R x and y equals to 0 means that the total absorption is R x y equal to 1 means total reflection. So, there are two means total absorptions when it is R x and y equal to 0, and when R x and y equal to 1, that is total reflection. So, the total values basically are, in case of binary example, varying between 0 and 1. So, we can call the intensity of a monochrome image, black and white image, or a binary image at coordinates x and y, the gray level L for an image of that point. So, now we can move further instead of just a binary image. So, L, we can say L equal to function f and x, and the interval of this L ranges between 0 L minus 1. So, where L equals to 0 indicates a black, and when L equals to 1 indicates the white. So, binary example is also here. All the intermediate values are shades of gray varying from black to white. So, two extremes 0 and 1, remaining values in between can have, but since we talk in terms of integers, so these values can, depending on the radiometric resolution or number of bits, these L equal to can be 255 and L equal to the 0. So, rest of the values can vary between 0 and 1. So, this is how the image is constructed. So, sampling and quantization are the two important processes used to convert a continuous surface into a digital image, and this quantization means assigning the number of bits per pixel, and sampling is basically indirectly it is controlling your spatial resolution. So, like here if I take a little different example, if this is continuous image which is shown here, if I take just a cross section and plot here, then this is the line scan between point A and B, and the white part is having of course very high values or reflection, then suddenly it drops, and then you are having curve like this, and again white part is having, then you reach to the B. So, this image sampling basically refers to the discretization. Instead of a continuous, now we are taking a profile or a cross section of a spatial coordinates. Coordinates are in terms of rows and columns along x axis, whereas quantization refers to the discretization of gray level values amplitude along y axis. So, here when we move here, this is what we are getting, the spatial coordinates starting from first column to the last column for this particular example, and the y axis here is referring to the amplitude or the pixel values which are being plotted here. So, by amplitude along the y axis is here. So, given a continuous image which is f, x and y, digitizing the coordinate values is called sampling, which is what exactly what we have done here, and the digitizing the amplitude, the intensity, the value basically plotting on the y using along the y axis is called the quantization. So, here the sampling and quantization, this is what we see, that after this at different location these values are collected and they are shown like this. So, here you get the from starting from here, then come here and then like this. So, this is a typical digital scan line, different pixels values are shown, and here both processes about sampling and quantization is also shown, that not continuous, but at certain intervals the data has been collected. So, that is sampling. So, if we go back again to this line which says a given a continuous image f, x and y, digitizing the coordinates value is called the sampling, and the digitizing the amplitude here, this is quantization, and the amplitude intensity value is called quantization. So, this is how an image is basically constructed and understood. Now, we have discussed about different sensors. We have also discussed about quantization and sampling, because if a sensor is on board of a satellite and having say 4000 CCDs in a linear array, then it is collecting the data in a continuous fashion and it is transmitting the data. Now, once the data has been acquired by the satellite or being acquired by the satellite, then what next happens? How we get the data from a satellite towards the earth? That is also important to discuss. This part is least discussed in remote sensing literature or elsewhere, because this we say it has been provided by an agency, like maybe agency might be NASA, agency might be ESA, or in our case in India agency might be NRSA, National Remote Sensing Agency. So, they provide, but how they really acquire the data from a satellite after this image has been acquired by a sensor, that is also important to understand. So, next few slides I am going to have the image acquisition basically from satellite to the earth, and for which you require a satellite earth station. And this is one example of satellite earth station of NOAA series of satellites, which at IIT Roorkee we are having and running since October 2002. It is having two major components. One is the external component, as you are seeing a antenna here, and another one is the internal component which is inside a lab and which is just PC based system, and the main here is the receiver. Now, the antenna which you are seeing in this NOAA case, it is 1.2 meter diameter parabolic disc antenna, and there is a motor here which is a 2 axis rotation motor. That means that it can rotate the antenna in if I say in horizontal plane in 360 degree, almost in 360 degree, and in vertical plane 180 degree. So, this disc is having capabilities of tracking any of these NOAA satellites which are in space, and whereas the internal component is having receiver. So, lot of cables are all connected with this one, and then one USB is in the system, and then there you are having a software which generally are called the grabber. One more important thing is another antenna which you can see here is the GPS antenna. So, two antennas outside and rest of the things are inside. Why this GPS antenna or GNSS antenna is, there are two purposes. One is to determine the location of this antenna on the globe, and second is to provide accurate timing to this receiving PC or computer. Because as you know that these computers, they are having for backup they are having a battery that may deteriorate with time, and the system clock may be delayed by few seconds or minute. Whereas for data acquisition from a satellite, that the system clock has to be very accurate as like atomic clocks, and which is only possible if we get the data from GNSS satellites or GNSS receiver. So, that is the purpose of installing. So, this antenna, GNSS antenna, keep watch on the watch of the computer, and whenever there is a delay or whatever changes in the system clock, it supersedes and correct the system clock. So, almost every minute this exercise is being done, so that the system remain completely coordinated with the satellites overpasses. So, we do not miss. Otherwise, what would be if there is a delay in our system clock, then the antenna would be locating the satellite as per the prediction program somewhere else in the space, that is 940 kilometer, 850 kilometer, and whereas the satellite might be at different location. So, if timing is perfect, then it works. So, this is how a PC based automatic, why automatic, that it is not necessary that whenever there is a overpass by NOAA series of satellite, one has to be present. System is always on, the power supply is always on, and whenever there is a overpass based on the prediction program, it goes in that direction from where the satellite will come. It align with the movement of the satellite and start getting the data line by line. It is a scanning devices on the NOAA satellite. So, this AVHRR sensor is scans line by line, and the data is transmitted directly towards the earth, and through these earth stations we can record the data. Since a spatial resolution is coarser in case of NOAA AVHRR, and therefore the swath is quite wide, I will be showing an image also. But the purpose of showing this map is that it is showing the location, this red dot is showing this IIT Roorkee satellite earth station, and a circle is there of 3000 kilometer radius. This is nothing but the footprint of a cone, base of a cone, and whose apex is in the suppose 850 kilometer with the satellite. So, if anywhere if you project this 3,000 kilometer radius circle in a space of 850 kilometer, then within that circle, if within that circle, if any NOAA series of satellites are coming, then our earth station can acquire the data. So, this base of cone one has to imagine in a space at 840 kilometer, and the apex of that cone is at IITR SAS location. So, anywhere within this circle, if satellite is overpassing, so if I project everything in a 2D, and if a satellite is here, and then our earth station can acquire data by tilting the antenna towards that direction from where the satellite would be coming, and it will keep tracking till that satellite disappears on the other side of the horizon, and this is done all automatically. That is why it is auto. See, sometimes you may get a image something like this, which has been acquired by our own satellite earth station, which has covered the entire Himalaya, because the spatial resolution is coarser, and therefore the swath width is very wide, 2800 kilometer, and in one go almost entire Himalaya has been acquired. But if suppose it would have been a 1 meter resolution instead of 1100 meter resolution, then only a very tiny part of the earth would have been covered, a very small strip, though at higher spatial resolution. So, there is always trade off between spatial resolution and the swath. Now, since NOAA AVHRR sensors are having two thermal channels, and therefore, it is possible to acquire data even in night time. This is not common with many satellites, because if they do not have the thermal channel, then the data cannot be acquired in night time. But NOAA is having thermal channels and this near infrared and two thermal channels. So, 3 channels data can also be acquired in night time, whereas in daytime 5 channel data, 2 visible, 1 near infrared and 2 thermal channel data can be acquired. So, this is one example. In the daytime the 1432 hours, and this is 23 hours in night time 11 p.m. and this is one of the thermal image which you see, and it is just like X-ray, seems to be X-ray, but it is a thermal image of the same part of the earth as seen in the daytime. So, that makes a big advantage if a sensor is having thermal channels as well. NOAA satellites is having, also your Landsat and this OLI series is also having, but normally they do not acquire data in night time, only the daytime thermal data is acquired. But in case of NOAA OHRR, nighttime data is easy to acquire because it covers a wide swath, and sometimes it is very useful. We have been using this thermal data for various purposes, especially in case of detection of pre-earthquake thermal anomalies. So, this brings to the end of the discussion about how different sensors are there from little electronics point of view, not in much detail, and then how the data from satellite to earth, how it comes through a satellite earth station, that part we have discussed. So, thank you very much.